So what's the beta En? Okay, and what we're going to derive is what's called the cross-entropy error. Okay, and it's going to actually solve both of these problems. Okay, it's going to be mathematically much more convenient, and the derivation is going to intimately use the probabilistic nature of h of x. Okay, and in order to derive this cross-entropy error, okay, I'm even going to introduce you to a new sort of concept called the likelihood. Okay, so the first thing we have to remember is, we have our data set. Let me tell you what the cross-entropy error is. So the cross-entropy error, so at least you know where we're going. Okay, so E in of W is 1 over n of the sum from n equals 1 to big N of the log of 1 plus e to the minus yn times W transpose xn. That is the cross-entropy error. I'll put it in a box. Okay, and we're going to derive that guy. But you might first ask yourself, why? That looks so ugly and complicated, Look, it's got logarithms, exponentials, and so on and so forth. This is a much simpler looking, cleaner error function. Okay, and yes, it might look ugly and more complicated, and it has logarithms and exponentials, but we don't care about how things look. Okay, we don't care about how things look. It's how they behave. It's and in particular how they behave when we want to now find the weights that minimize the error function, and also comes with a probabilistic interpretation. So it's ugly, but that's the guy we want. Okay, ugly but behaves well. Okay, so let me go back to the data. We're going to derive this error function. It's going to be mathematically convenient, and it's going to have a probabilistic interpretation. So it's going to solve both of these problems, and in order to derive this, we're going to have to go back to the data. So the data. And I want to remind you, so the data is x1, y1, x2, y2, xn, yn. Okay, good. And remember x, n, y, big N. And remember y, little n. So I'm going to use little n to index and big N for the number of data points. So y little n is in -1 or +1. But all those details are not what I'm trying to focus on at the moment. I want to focus on the fact that, these data points are IID. So the data is IID. Okay, and so independent, identically distributed. And you might say, why? How do we know that? Okay, so I'm going to pause the video. And, or you can pause the video and think to yourself, why is the data independent, identically distributed? Are we guaranteed that? So we pause the video. And if you're coming back and you said, well, that was one of the foundations, one of the pillars of the theory that we needed in order to establish that learning is feasible. To get this link from E in to E out, we needed the fact that the data is IID, independent, identically distributed. And when you go to your client and your client says, okay, I've got a data set, you first ask them, did you generate these data points IID? Okay, so we're implicitly assuming that we're in the setting where, it's a good thing to minimize the in-sample error, whatever it is. And it's a good thing to minimize the in-sample error only when you've got the link from E into E out. Okay, and to have that link from E into E out, one of the conditions is your data must be IID. Don't ever forget that. Fundamental. Okay, so we can assume the data is IID. Okay, and so we can ask, what is the probability that you observe the values y1, y2 up to yn, given that, the data point inputs are x1 up to xn. So what x1 up to xn? So what is the probability of y1, y2 up to yn, given that they're occurring on the inputs x1, x2 up to xn? Okay, now you might ask, well, why are we doing this? Okay, so you'll see shortly. So this quantity here is called the likelihood. It's the probability. Think of it as the probability of obtaining the data. Think of it as the probability of obtaining the data. So you've generated the x values, and we're asking what is the probability that you observe the specific y values that you observe. Now, why are we focusing on the specific y values? Because, what we're trying to learn is a way to predict the y values. We're trying to learn the probability of the y values given the x values. That's what h of x is. That's what f of x is. Okay. And if our h of x is approximately equal to f of x, then, this probability, okay, is equal to the probability of y1 given x1 times the probability of y2 given x2 times the probability of yn given xn. Okay, and you might say, well, why is that? IID, the data are independent. And we will write this as the product from little n equals 1 to big N of the probability of y little n given x little n. Okay. So that's the probability of observing the data. And that's exactly where the h comes in. Okay. So the hypothesis that we're ultimately going to produce, okay, has to be, if it's close to f, is exactly capturing this guy. So this guy, okay, is supposed to be h of xn, okay, if yn equals plus 1, and 1 minus h of xn if yn equals minus 1. Okay? Because that's what h is. It is the probability of observing y given x. Okay. And here we are intimately using the probabilistic interpretation of h, the fact that h is outputting a probability. So there, we're fundamentally using the fact that h is outputting a probability. Okay, now it's going to be convenient to have a more compact way of saying this. Okay, so let's now specialize to our choice of h. So h of xn is equal to theta of w transpose xn. Okay, and 1 minus h of xn is equal to 1 minus theta of w transpose xn. Now, if you remember, I told you that the choice of the sigmoid that we made is going to be very mathematically convenient, and here we're going to reap some of that payday because, one of the properties of the sigmoid that we, chose, and you can look back in your notes, one of the properties of this sigmoid is that this is equal to theta of minus w transpose xn. Okay. And this is because theta of minus s equals 1 minus theta of s. So there, we're already benefiting from our particular choice of sigmoid. Okay, so if yn equals plus 1, this is supposed to equal theta of w transpose xn, and if yn equals minus 1, this is supposed to equal theta of theta of minus w transpose xn. But look, when yn is plus, this is plus inside here. When yn is minus, this is minus inside here. So we can summarize both of these equations as theta of yn w transpose xn. Okay? So when yn is plus, this is plus, and we get that. When yn is minus, this is minus, and we get that. So it's a very convenient form. So there's nothing mathematical here. It's just a convenient way of summarizing this fact. It's just a convenient way of summarizing this fact. Okay? And it has to do with the choice of sigmoid. If you are perfectly welcome to choose a different sigmoid if you want, but then this nice convenient, representation of this fact won't be possible. And so the derivation will still be valid, but the algebra won't be as compact. Okay? So this means that we can replace the probability of yn given xn by theta of yn theta of yn times w transpose xn. Okay. So this guy here is exactly theta of yn w transpose xn. Okay. It's just a mathematical fact due to the choice of our sigmoid theta. Okay. So let's erase that justification. Okay, so the probability of observing the y-ends for these particular xn's that were generated is the product of the probabilities, which is equal to the product of theta evaluated at yn w transpose xn. Okie dokie. So this is called the likelihood. Okay, I've derived the likelihood. Well, what use is the likelihood? Okay, now let me go back and tell you again what was the likelihood. It was the probability of observing the y values given the x values. And if your hypothesis H were f, so if it approximates f, then the probability of obtaining the data should be high. And if it were not close to f, then it's not going to have a high probability for you to observe the data. Okay, so the natural thing to do is to find the choice of weights w that maximizes the probability of observing the data. So choose the weights w to maximize the probability, the chances to observe the data. Okay. Now, this is called the method of maximum likelihood. So this is called the method of maximum likelihood. And the philosophical debate on whether or not this is the right thing to do, well, it's ongoing. Okay? And there are ways we can justify it, there are ways we can poke holes at this. Okay? And that's not our business. We're going to leave that to the philosophers of mathematics, the philosophers of probability theory, and let them have it out with each other as to whether or not, oh, this is a good thing. The bottom line is, it intuitively makes sense to maximize the likelihood because a good hypothesis should produce data with high probability, okay, because the probability should be large when the y's are +1, and the probability should be large. So the probability of observing the y values should be large, no matter whether the y's are +1 or -1. Okay, so a good hypothesis definitely should, a good hypothesis definitely should have a high probability, and so whether we should maximize the probability or should we do something else, well, okay, that's up to the mathematicians. But it's a very popular approach, okay, the method of maximum likelihood. And so we're going to borrow this approach from the math side, from the probability side, and just use it. Okay, so the prescription is to choose the weights w that maximize the probability to observe the data. Okay, so how do we do that? So let me call this thing the likelihood, okay, L. And the prescription is to pick the weights w to maximize L, the likelihood. How do we do that? Well, it looks complicated. You have to find the weights w that maximizes this complex product. Okay, but now I'm going to show you a sequence of mathematical facts, and now here there's no, assumption, or there's no, is this the right thing to do? It's just these are mathematical facts. Mathematical facts. Okay, so if you have any function, let me call it, for argument's sake, let me call it L of w. Just like here, we have a function L of w. Well, it also depends on the data, x and y, but that's fixed. So materially, as far as we're concerned, it depends on the weights w. So you have a function L of w, and you want to maximize with respect to w. Okay, that's equivalent to maximizing the logarithm. Maximize. So, you want to find the w which is which maximizes this. So actually, technically, I should say you want argmax with respect to w of L of w. So you want the w that maximizes this. That's equivalent to finding the argmax with respect to w of log L of w. That's just a mathematical fact, and that's because the logarithm is an increasing function, and you can do this as long as this function L is positive. And it is the case that our function L is positive because our theta is a positive value. So it's a product of numbers between 0 and 1, and that product can be small, but it's positive. So we can take the logarithm of this and find the argmax, maximize with respect to W. But it's also a mathematical fact that if you're maximizing any function, you can maximize any constant times the function. Okay, so this is the same as finding the argmax with respect to W of 1 over n times the log of this function. Okay. Now, a twist. Okay. Finding the maximum of some function, okay, or the argument of the function that attains that maximum is equivalent to finding the minimum of that function. Actually, the argument of that function that attains the minimum if you look at the negative of the function. So this is equivalent to the arg min over W of minus 1 over n log of L of W. Okay. So these are just mathematical facts. Okay. Can't argue with them. If I want to maximize a function, I can maximize its log and find the argument that maximizes the log. I can maximize any constant times the function, or I can minimize the negative of the function. Okay. And you might ask, why am I doing this? Well, most of the stuff I'm doing is just cosmetic, but the main thing here was introducing the log. And can anyone tell me why I introduced the log? Pause for 1 second. We'll come back. I introduced the log because the log is this beautiful function that can convert a product into a sum. Okay. So the prescription, which is to choose the weights W that maximize the likelihood, has now translated into the prescription choose the weights W to minimize minus 1 over n times the log of L. And I want to emphasize that that prescription and this prescription are the same prescription. Okay. They will produce the same weights W. Okay. And why are we doing this? Because that makes intuitive sense. It's the method of maximum likelihood that's popular in statistical inference. It's not our business to philosophize on whether it's proper. We're just going to borrow the fact that maximizing likelihood is a good thing to do. Okay, and this is the likelihood. So let's see where it takes us. Okay, so we want to minimize what? We want to minimize this guy. So we want to minimize minus 1 over n, the logarithm of the likelihood. But I already told you why we introduced the logarithm, because the logarithm of this product becomes a sum of logarithms. So we want to minimize minus 1 over n, the sum from little n equals 1 to big N of the log of theta of yn W transpose xn. Now we can take this minus sign inside the log, inside the sum, and then you have minus log of something is the same as log of 1 over something. So this is equal to 1 over n, the sum from n equals 1 to big N, minus log of theta, which is log of 1 over theta, yn W transpose xn. But 1 over theta, the other nice mathematical property of theta that I mentioned before, anyone remember what it was? 1 over theta is 1 plus e to the minus theta. So this is 1 over n, the sum from little n equals 1 to big N of the log of 1 over theta, which is 1 plus e to the minus yn W transpose xn. There. That's exactly the in-sample error that I claimed we were going to derive. We have derived the cross-entropy error. Wonderful. Wunderbar. Okay. So, what was the prescription? Okay. The prescription was the learning process. Okay, you can think of this as the training process. So how do you pick your final hypothesis G? Choose the weights W that minimize this in-sample error. Okay. Choose the weights W that minimize this in-sample error. And we just derived it. So choose weights W to minimize this in-sample error. And that's a good thing to do. It intimately uses the probabilistic nature of H in deriving it, and it'll also be mathematically very convenient. Okay. So, How are we going to do that?
So let's ask 3 questions.
Or 2 questions.